Hi, in this video I'll be talking about an efficient decoder for linear distance quantum LDPC code. You can find the full version of our paper in the archive. So first let me begin by defining a quantum code. Our quantum code are code states, which is the subspace of the n-qubit Hilbert space, that are the simultaneous plus one eigen cats of some abelian group. So this is defined by two pieces of data, the X check matrix and the Z check matrix. These are matrices over F2, such that each row of the Z check matrix and each row of the X check matrix are orthogonal. So when we define our stabilizers, we're going to define an X and a Z stabilizer, which is just given by the rows of our X and Z check matrices, respectively. And then our stabilizer group is just the group generated by the rows of these things. So it's convenient to define these two classical codes, the X and Z codes, which are just given by the kernels of the X and Z check matrices considered as classical codes. And our code distance is just the minimum weight string that's in the X code, but is not a Z check, or something that's in our Z code, but is not an X check. So our code is said to be an LDPC code if our X and Z checks have a constant size row and column weight. And this is actually really useful for fault tolerance because every quantum LDPC code has a fault tolerant implementation. So in particular, we'd like the best possible distance and rate. And this was recently shown to be achievable by Kalchev and Panteleev, who constructed a quantum LDPC code with linear distance and constant rate. Recently, there was an alternative construction by Levery and Zemmour, the quantum Tanner codes, which I'll present here in a moment as we build on them. And before this work, no decoder for a good quantum LDPC code was known. So here's our main result. The parameters are not important, but the important part is that we have constant rate and linear distance such that we have a linear time decoder that corrects up to some fraction of the distance. So let me define the quantum Tanner codes. So you might recall the work of Sipser and Spillman, the expander codes. And in Sipser and Spillman, what they did was they added some local constraints to a graph. So you associate each edge, to each edge you associate a bit, and then around each vertex you impose constraints that are local with respect to the graph. So we'll do something similar for the construction of the quantum Tanner codes, but we need some extra structure. In particular, we require that our checks have to commute so that we have a valid quantum code. So we're going to need something extra than besides just a graph. We're still going to use a small classical code. We're still going to have the local codes, but we're going to need a kind of different expanding object. And this is, you can think of it as a graph with squares. So in addition to vertices and edges, we're actually going to have these squares, which are we're going to call faces. So the object that we use is this left-right Cayley complex, which first appeared in the construction of good locally testable codes. And so fix a group and fix two generating sets that generate this group, satisfying this technical condition. Then what we're going to consider is the Cayley graph given by acting from the left with the first generating set and acting from the right with the second generating set. And if this Cayley graph is not bipartite, then we're just going to take the double cover. So in particular, this thing has a lot of structure. We already have two types of vertices and two types of edges. And actually we have these faces now, which is specified by a tuple. We take a group element and then a generator from the A set and a generator from the B set, and that specifies this face. And this is a well-defined quantity because of this earlier condition. So we define this left-right Cayley complex, which is has the vertex set, our two types of vertices, our two types of edges, and now faces. And what's going to be important later is these two graphs that we can define on this complex, which is either the one of our two vertex colorings, and the edges are the faces of the complex. And what's relevant is that these graphs have good spectral expansion if the original Cayley graphs did. So you can see that this is actually a well-defined graph because our faces are well-defined. So I'm going to attach to every face a qubit, and then much like in Sipser-Spillman, we're going to impose X or Z checks on the vertices of these G-squared graphs. And the local view now is going to be all the faces that are incident to a vertex. So in particular, our X and Z checks, our X and Z codes are going to actually be classical Tanner codes defined with respect to our two square graphs, G0 square and G1 square. And just to be precise, something is in the code space of our X code if and only if around each vertex of G0 square, we see a code word of the local code. And this is exactly the same for the Z check matrix with G square 1 and with a different local code. So, okay, I need to tell you a little bit more about what our local codes are. So first note that the local view is this matrix given by indexing into it by elements of A and B. So our A and B sets are kind of like rows and columns. So we can arrange here, I've taken the local view of a particular vertex, and I've illustrated all the generators that are incident to it, the edges, and it's got a bunch of faces that are incident to it. So we can lay this out nicely into something that looks like a matrix. And if we pick a particular element out of the A set and out of the B set, this picks a particular entry of the matrix, so we can kind of index into it. And what's also important is that if we pick a single element of A, a single element, or a single element of B, and some group elements and some vertex, this looks like pages of the book. And each edge goes between two local views that impose checks of opposite types. So we need to look at these edges and pick our codes such that our checks commute when only restricted to the faces that are incident to an edge, so these pages. So the codes that we're going to pick are related to classical Tanner codes. So just pick two classical codes and impose the following constraints that are just picked from the tensor code and the tensor code of the dual codes. So our local code is this funny looking thing. It's just the dual of our tensor codes. And to convince you that this is a valid CSS code, we can just look at these checks. So if we pick a particular stabilizer generator, it's going to be in the tensor code at a V0 vertex. Now, if we look at the adjacent V1 vertex, what we see is, we look at this restriction, recall that this is just a row, we see the standard basis vector, tensor product, some code word. And this is in the local code, so our checks are orthogonal. We have a valid CSS code. So in our work, we prove improved robustness parameters. So similar statements were proven in Kalchev and Panteleev, their quantum LDPC code paper, and also Levery and Zemmour's quantum Tanner code paper. But it was for a robustness parameter that was slightly worse than delta to the 3/2. Our work strengthens the robustness parameter to strictly greater than delta to the 3/2, and that's necessary to achieve a simplified proof of the decoder and the code construction, the distance proof. So this was recently further improved to the best possible parameters by Jenner, Shea, Lin, and Vidic, and also Kalchev and Panteleev. So now let me move on to the decoding problem. So it suffices just to consider Z errors because the quantum Tanner codes are symmetric between X and Z. So the same proof will work for both cases. And we're also going to consider this just applied to the 0 code word. These are linear codes, so that's fine. And just as a reminder, these errors are detected at these V1 vertices, and that's just where the error is not in the local code. And so our task is given access to the syndrome, we want to output a correction such that our error plus the correction is equal to a stabilizer generator. In other words, that it's just equivalent to 0. And in our work, we're just going to take a greedy approach to this. This is kind of similar in spirit to Sipser-Spielman's flip, but there'll be some extra complications along the way. So first note that we have just this arbitrary choice of the basis of our constraints. So if in flip, you recall that you minimize the syndrome weight, but we can't do that here. So we have to define something else. And we're going to consider functions defined with respect to the local views. For an error, we're going to define its local potential at a vertex, just given by the distance from the local code. And this will be our analog of the syndrome weight. And then we're just going to sum them up to get this, what we define to be the global potential. And this is the thing that we minimize. So now I can state our algorithm. It's quite simple. We're just going to look for some vector to flip that's in some local view such that we strictly reduce the potential. And note that we're searching both in the V0 and the V1 local views. The V0 local view will come in later. These are the local views where there's some special structure because this is a quantum code. So the necessary main technical result will be to show that actually at each step that we can make forward progress, that we can find some flip set that strictly reduces the global potential. And this is the main tricky part. But once we have that, it's actually quite straightforward to prove that our decoder succeeds as long as the error is not too large. And the way we can do it is just by tracking the size of the flip sets, the sets that we flip, and compare that to the potential. And once we compare that against the distance, we can show that we cannot have applied a correction that takes us between two code words, so we must have corrected back to the nearest code word. And you'll note that actually this potential, we take a linear number of steps, and the potential can be at most linear in the error, the weight of the error, so our decoder must also be linear time. Now let me move on to a proof sketch of the main technical result. So first, to do this, we'll define this local minimum weight correction. So consider an error, and for each local view, we're going to look at the closest code word to the error on that local view. And we're going to define this local minimum weight correction that's just the difference between the closest code word and the error. And so this is something that's well defined because we can get this just by running just by brute force, a minimum weight decoder for the local code. And then we're just going to take the union for this thing that we're calling the total correction, this R set. And this R set's really the thing that's at the heart of our proof. We'll use it in the next step quite a lot. So you'll notice that actually the local potential is actually just the weight of these local minimum weight corrections, and then the global potential is kind of upper bounded by the size of this R set. And our goal is to reduce this global potential. Our proof proceeds in three main cases. In the first case, we're just going to flip single bits. And if that's not possible, that allows this R set to be viewed as a directed graph. The orientation tells us which a particular edge, which local view it came from. And that's going to allow us to sort of add bits to flip bits, which may not change the global potential, but if we flip many bits at once, that will allow us to do something. And so that's case two. So this R set might have a high overlap with the code word of the local code in some local view, and then we can find some flip set that's related to that code word to reduce the local potential. So what that looks like is as follows. First, we can relate the local view to a configuration where we've shoved all the weight, or most of the weight, to all the neighboring local views. And so in terms of the orientation of R now, is they're all pointed at our local view. And then we're going to find this nearest code word to the R set, and then we're going to flip it. And what that allows us to do is to transfer weight from the surrounding local views to our local view. But because we added the code word, we're not going to change the weight on our local view, the central local view, as much as we reduce the weight from all the neighboring ones. So in this example, we've just decreased the total potential just by 1. Now, in the third case, this is by far the most involved case, and this is where we have to start looking at the V0 views. And we have a lot of structure that we've now proven about this RSAT in this case. The way we proceed is that noting that the error resembles a code word on all of our local views. So what we're going to do is we're just going to apply a similar argument similar to the original distance proof. And either a flip set exists within some V0 local view, or that we can reduce the error weight by adding a Z stabilizer. Without loss of generality, we can assume that, that this second case is not possible. So what we conclude is that a flip set must exist. And the way we prove this is we use the expansion of the left-right Cayley complex and the robustness of our local code. And the thing that we show is that this error must be clustered in a particular way, and this required our improved robustness result that we proved earlier. So this is where things become involved. So to summarize, we've shown the existence of a decoder for the quantum Tanner code, and our decoder has linear runtime, and it provably corrects all errors up to some constant fraction of the code distance. There's still some open questions. Our decoder has some quite nasty constants hidden inside the big O, and we'd like to reduce those. And then in addition, it's of practical interest if we can have smaller code constructions, maybe ones that get rid of the local code, because that will simplify things quite a bit. And finally, we'd like a decoder that can tolerate measurement errors, because we've assumed that our syndrome is noiseless, but in an actual experiment, our syndrome might be noisy, because our circuit that measures the syndrome might itself have faults. So we have to be able to tolerate that. So with that, I'd like to conclude.